So far with subtopic 11.2 on power generation and transmission, we've been looking at more the power generation side of things. Now we're going to start to have a look at a bit more at the transmission. And the first thing we're going to look at with the transmission is a transformer. Now a transformer is a device that's used to basically increase or decrease potential difference. And so it's a device in which an input potential difference can be either increased or decreased. And which one of those, whether it's going to be increased or decreased, will depend on the purpose of the transformer, where it's being used, increased or decreased. Ultimately, as with a lot of devices, they vary in size and shape. We'll have a look at a couple that we have in our prep room, and as well as varying in size and shape, they can be used in both very high and very low power situations. So across a broad range of applications. However, they basically have the same structure. So regardless of where or how they're being used, and in order to show that structure out, rather than just sort of list it out, we're going to have a look at a diagram. And here's one I prepared earlier. So the general structure here that we need to look at is as follows. On the left-hand side, we have the input coil, that's otherwise known as the primary coil. So that's this one on the left-hand side. And on the right-hand side, we have the output coil, or the secondary coil. A couple of properties about the input and output coils that are important. We have an input potential difference here, so we're going to call that on Vp for V primary, and we would then get an output of Vs, so the potential difference across the secondary. You'll notice here too that the number of coils, or number of turns of the coil on each of these, the primary and the secondary, is different. So in the primary coil we'd be interested in the number of coils that would be Np, and in the secondary it'll be Ns. We'll come back to that a bit later when we start looking at some of the ins and outs of how this operates. Now the other thing that's important here is this grey thing in the middle, and it's known as an iron core. And the iron core is basically acting as a soft magnet. The other important point, this potential that we've got, Vp, need to keep in mind that that's actually an alternating potential difference. So it would have a maximum value of Vp, so that value Vp is the peak, and then likewise we'd get an output that would be an alternating potential as well, and that would have a peak of Vs. So these values of Vp and Vs are the peaks, they're not the RMS values. Just as a quick side note, if you were looking at a circuit symbol for a transformer, the circuit symbol looks something like this, so it represents both the input and the output coils with the iron core in the middle there, so that's our circuit symbol. Now, the way that this then operates, a very brief statement here, and if we need to we can go over this in more detail to really bed down the operation of a transformer, but I'll just summarize it very briefly here. So initially we have a current in the primary coil. Now because we've had a look at electromagnetic induction, we know that if there is a current through a coil, that produces an alternating magnetic field. So we know that a current in a conductor produces a magnetic field, and now we've got this alternating current. It's going to produce an alternating magnetic field, and that magnetic field will be experienced in the coil, or produced in the core, sorry. And that magnetic field then sort of loops all the way around the core and starts to thread through the secondary coil, and so that is going to induce an EMF in the secondary coil. So there's a very brief statement. We could go through that in much more detail and look at each one of those statements in far greater detail, but I'll just leave it at that, and if you need any extra help with that, then you can just let me know. Notice here that I've said we're only looking at the EMF in the secondary coil. If we connected that secondary coil to some other component and created a circuit, then we would also have a current flowing. We'll come back to that later, but just wanted to mention that in passing. Now, to take that a step further and start to look at some of the calculations that sit behind this, an input potential difference with a maximum of Vp, or with a peak of Vp, is going to produce a flux phi and that flux will be produced in the core itself. And as a result, we're going to see that flux, because the input is an alternating input, then the flux will also be alternating. The secondary coil is then going to experience that flux as well, and it will therefore have a flux linkage. And if you recall, flux linkage is the number of coils multiplied by the flux itself. So that has a flux linkage of Ns times phi. So the EMF produced, the secondary EMF, is given by Faraday's law, and the equation for that will then be the EMF in the secondary coil will be negative Ns delta phi on delta T. So there's the secondary EMF that's produced. There is actually also a flux linkage in the primary coil as well. Now this might seem a little bit odd to suggest that there's a flux linkage of Np phi in the primary coil, considering that it was the primary coil, or the current in the primary coil, that produced the flux in the first place. So even though that potential Vp is inducing the flux, however, because of that, we get an EMF that's known as a back EMF. So in other words, the potential difference that's producing the flux actually creates an EMF in the same coil, and that back EMF is induced in the primary coil. Sorry, the back EMF is induced. And what we will see is that the EMF for the primary coil is somewhat similar, just that we have these primary coil quantities instead. Now, what you will hopefully notice is that both of these terms have the same rate of change of flux, so delta phi and delta T. So we can equate these two together. So since both experience that same change in flux, what we can say then, and I'll take the negative with the flux itself, so we'll keep that negative with the delta phi and delta t. So negative delta phi and delta t is then equal to the EMF in the primary coil divided by the number of coils in the primary coil, number of turns, and that's also then equal to the EMF in the secondary coil divided by the number of turns in the secondary coil. So if we want to then take that a step further, we could say that the EMF in the primary coil compared to the EMF in the secondary coil is in the same ratio as the turns in the primary coil over the turns in the secondary coil. Now that equation is just part of one of the equations that's in the data booklet, so we'll come back to it and look at it in a slightly different sense in the next video. But before we do, let's just look at one last thing with this part of the equation. If we look at the resistance in the coils, so if those resistances are negligible, then what we can say is that the EMF that's produced in both the secondary and primary coils is then related to the peak voltage. So we can say that EMF in the primary over the EMF in the secondary is the same as the potential difference across the primary coil and the potential difference induced in the secondary coil. That's not actually part of the data booklet, but in order to just sort of link back to that idea, and I'll sort of come back up again in the next video as well, if we then have a given value, or given peak value Vp, we then have, and considering that that would then also be equal to Np over Ns, we can then say that if Ns, so the number of coils in the secondary, number of turns in the secondary coil, is greater than the number of turns in the primary coil, then we're going to see that we'd have that the voltage, or the potential difference across the secondary coil, will be greater than the potential difference across the primary coil. This is known as a step-up transformer, because it's taking that input potential difference and it's increasing it. Conversely, if Ns is less than Np, then the secondary potential difference is going to be smaller than the primary, and so this is known as a step-down transformer. Now, the reason why we need step-up and step-down transformers we'll have a look at in the next video, where we start to look in a little bit more detail at how power is transmitted and why transformers are important in that process.